Hello everyone. This lecture is exclusively recorded for first year BSc student of BK Birla College Kalyan. In last lecture we have seen the property of sequence, that is whenever sequence is convergent then it converges to unique limit. Today we will explore few more properties of sequences, that is every convergent sequence is bounded and the algebra of sequences. We have already seen the definition of bounded sequence. Now we will prove the result called as every convergent sequence is bounded. Result, every convergent sequence is bounded. So let's prove. It is given that uh, sequence xn is convergent, say converges to a real number p. So that is xn converges to p. We have to show that the sequence xn is bounded. So when sequence xn is convergent to p, so by definition of convergence, we can say that for all epsilon greater than 0, there exists n naught, a natural number, belongs to R, belongs to natural number, such that mod xn minus p is less than epsilon for all n greater than equal to n naught. When this is true for any epsilon, any positive real number, so take epsilon in particularly as 1, which is greater than 0, then the above result will be follow. So xn minus p will be less than 1 for all n greater than equal to n naught. Let me call this as number 1. I have to show that the sequence xn is bounded. That means we have to show that sequence xn is bounded. That means the modulus of sequence mod xn is less than some constant. That is what I need to prove. So let me start with consider mod of xn. Mod of xn is same as mod xn minus p plus p. I can apply the triangle inequality. So it is xn minus p plus mod p. But xn minus p from 1, it is less than epsilon, less than 1 plus mod p whenever n greater than equal to n naught. So what I got is as follows. I got mod xn is strictly less than 1 plus mod p for all n greater than equal to n naught. So you can see that this is a constant and the mod xn is means x1 is less than 1 plus mod p, x2 is less than 1 plus mod p, so on and so forth. Or instead of saying that, what I will say, this is true only if my n is greater than equal to n naught. So for which value of n it is 2. So you can observe that this relation, this inequality holds for all those n which are above the n naught. That means x n naught plus 1, you could see that this holds for x naught n plus 1 is less than 1 plus mod p. Similarly, x n naught plus 2 is less than 1 plus mod p. Similarly, x n naught plus 3 is less than 1 plus mod p. So which natural numbers this inequality covers? It covers all the natural number which are above the n naught. It cannot guarantees the natural number which are below the n naught. So what are the natural number before n naught? 1, 2, 3, 4 up to n naught minus 1. These natural numbers are not guaranteed by this. So what we will do? So I wanted to write down, instead of saying this, I want mod xn should be less than a constant for all natural number. Now here I got mod xn is less than constant only for those natural number, which are above n naught. So I am interested to have the those natural number. For any natural number the inequality holds. So I will going to do one small trick in this. This is, I don't need this because I hope this much this you must have understood. So the trick which I will be going to do is as follows. I'll take capital M as maximum of mod xn mod x2 up to mod x naught minus 1. So those number itself I will take, and then this 1 plus mod p is already there. So that means all the natural number I am covering, because x1 to n naught minus 1 and 1 plus mod p will be covered, will be all the n naught onwards natural number will be covered because of 1 by mod p. So if I take this, then I can say that mod xn is definitely less than equal to m maximum for all n belongs to natural number. So this would imply sequence xn is bounded. So it's very important here. Whenever sequence is convergent, it is always bounded. Hence proved. Hence proved. So the remark or note of this: the converse of the theorem is not true. The converse of above theorem is not true. That means if sequence xn is converges to p, then we cannot say the converse is, if the sequence xn is bounded, if sequence xn is bounded, that does not implies the sequence xn is convergent. So if the converse is not true, I should give a counter example to justify the converse. So I need to give a counter example where the sequence is bounded but it is not convergent. So let us take xn, the sequence xn, as the nth term of the sequence is minus 1 to the power n. You could see that this sequence will be have a two terms, plus 1 minus 1 plus 1 minus 1. For the even n it is plus 1, and for the minus for the odd n it is minus 1. You could see that if I take the even sequence, even term only, then it converges to plus 1. It is constant sequence. And if I take the only odd terms, then it will converges to minus 1. So you could see that sequence has a two limit, and whenever sequence has two limit, then whenever sequence is convergent, it has to be unique limit. Well, I will be using a epsilon approach to prove this. That is just a small thought one can think about. Maybe in upcoming lectures, I will show that this sequence is not convergent with the help of subsequences and all. We'll explore that little later. But now, how will I show that this sequence is not convergent? So this sequence is bounded, but it is not convergent. That is what I need to show. Is this a bounded? What is mod of xn? Mod of xn is minus 1 to the power n. So it is clearly plus 1. And plus 1, if it is a constant, so you can say that it is always less than equal to 1. So mod xn is less than equal to 1 implies sequence xn is bounded. Now we have to show that the sequence xn is not convergent. So this is not true. Xn is not convergent. So how will you prove? Suppose sequence xn is convergent. So let's assume that it is convergent. Say converges to P, that is xn converges to P. By definition of convergent sequence, we say for all epsilon greater than 0, there exists a naught belongs to natural number such that modulus of xn minus P less than epsilon for all n greater than equal to n naught. So you take this as number 1. So what I'll do, take epsilon is equal to 1. Right. So if I take epsilon is equal to 1, then the equation number 1, that inequality number 1 becomes xn minus p, which is same as my xn is minus 1 raised to 1 minus p is less than 1. This is number 2. Now this inequality holds for all n greater than equal to n naught. So uh, let me take in particular instead of saying this n. So I will say in particular this is n naught. So n is n naught I will say. And similarly this will also will be useful for the n naught plus 1 also, because you take any n which is above n naught, this inequality will hold. So x n naught plus 1 minus p is equal to modulus of minus 1 as to n naught plus 1 minus p. This is also less than 1. Right. Now what I'll do, I'll consider modulus of minus 1 as to n naught minus minus 1 as to n naught plus 1. Now what I'll do, I'll add and subtract p. So if I add and subtract p, what I'll get? So I will subtract p plus p minus of minus 1 as to n naught plus 1. Use the triangle inequality. So you will have minus 1 as to n naught minus p plus p minus minus 1 as to n naught plus 1. But this is number 1 and 2 says that okay, this is 3. From 2 and 3 we can say that this is less than 1 plus 1 from 2 and 3. So basically I have shown that it is true. So what I have shown is as follows: modulus of minus 1 power to the power n naught minus 1 to the power n naught plus 1 is less than 2, but this is same as minus 1 to the power n naught. This is plus minus 1 to the power n naught less than 2, because minus 1 to the power n naught plus 1 can be written as minus 1 to the power n naught into minus 1, and that minus minus will become plus. So I will have 2 times minus 1 raised to n naught is less than 2, which is 2 times modulus of minus 1 raised to n naught less than 2. But minus 1 raised to n naught will be modulus of this is always plus 1 only. So I will get 2 less than 2, which is a contradiction, and I got contradiction because we assume that minus 1 raised to n is convergent. So hence sequence minus 1 raised to n is divergent. This is very interesting sequence because many a times we will prove that this helps a lot in a many counter examples. So in upcoming lectures in algebra of sequences and all, we will definitely take the help of this sequence. So let me prove the algebra of sequence now. There are few algebras. So algebra of convergent sequence. So theorem, if xn converges to p, yn converges to q, then prove that xn plus yn converges to p plus q. Proof, it is given that xn converges to p. So we can apply the epsilon definition. So this would imply for every epsilon greater than 0, there exists n naught belongs to natural number. So maybe I have yn also. So for yn also I will be using n naught. So instead of n naught I will say n1 and n2. There is n1 belongs to natural number such that mod of xn minus p less than epsilon for all n greater than equal to n naught. Let me call this as number 1. Also, it is given that yn converges to q. Yes, yeah. So what does this mean? This would imply for every epsilon greater than 0, there exists n2 belongs to natural number such that mod yn minus q is less than epsilon for all n greater than equal to n2. This is number 2. So we have to take a common n naught which should holds 1 as well as 2. So to have the common n naught, the general methods or choices, take n naught is equal to maximum of n1 comma n2. That would imply n naught greater than equal to n1 and n naught greater than equal to n2. So this would imply 1 and 2 holds. So 1 and 2 can be replaced, n1 and n2 can be in 1 and 2, n1 and n2 can be replaced by n naught. That is what it says. I have done one small mistake here. Here I wrote n1 only. So n naught, so I should say n1, similarly n2. Now I need to show that xn plus yn converges to p plus q. So basically I need to show that the difference between xn plus yn and p plus q is less than epsilon. So let us consider that difference. So consider modulus of xn plus yn minus p plus q. This difference will be as follows. This will be xn minus p plus yn minus q. This is how the difference will be. Apply the triangle inequality, you'll get xn minus p plus modulus yn minus q. But this is already less than epsilon. This is also less than epsilon. This holds only if for all n greater than equal to n naught. Now I am not saying n1 and n2 because this n naught will holds the number 1 as well as number 2. So this is a common n naught which will work for 1 and 2. So I will get 2 epsilon whereas I want only epsilon. So what I'll do, I'll make here epsilon by 2 because epsilon is in our hand. Here also it is epsilon by 2. So if I take epsilon by 2, I will have epsilon by 2 epsilon. So which is epsilon. So what I got is as follows. Therefore, modulus of xn plus yn minus p minus q less than epsilon whenever n greater than equal to n naught. Right. So this would imply sequence xn plus yn converges to p plus q. Okay. The converse of above theorem is not to remark. The converse of above theorem is not true. If the converse is not true, I should give a counter example. So let's write down the counter example. So I need to give a counter example where xn plus yn is convergent, but at least one of the xn and yn is not convergent. So what I'll do, I'll take xn as minus 1 raised to n and yn as minus of minus 1 raised to n. So if you take xn plus yn, then it will be 0 and it is a constant sequence. So sequence xn plus yn, which is a singleton 0, is constant sequence, and constant sequence is convergent, which is convergent. And where does it converge? In fact, constant sequence converges to that number itself. So xn plus yn will converge to 0 only, right? But xn plus yn is convergent, but the individual, neither xn is convergent nor yn is convergent, but xn and yn are divergent. So we have proved that the converse is not true by an appropriate counter example. Algebra property number 2. If xn converges to p, yn converges to q, then xn minus yn converges to p minus q. The proof goes exactly similar to what I have done in 1. So I am not doing that. It could be a good homework. Of course, the converse of this number 2 is also not true. The same counter example will work. Or maybe you take xn and yn, both are same. Xn you take it as minus 1 to the power n, and yn also you take minus 1 to the power n. So for these two sequences, their subtractions is again 0. And since the subtraction is 0, implies that the sequence is constant. So subtraction is convergent, but the individual sequence is not convergent. Property number 3. If xn converges to p, then alpha times xn converges to alpha times p, where alpha belongs to R. So if you multiply scalar times a sequence, then it will converge to scalar times that limit only. So proof: if alpha is equal to 0, then alpha xn will be 0, so which is constant sequence. And converges to 0. 0. That is, yeah, this 0 can be written as 0 alpha times p, where alpha is 0 times p. So you could see that alpha xn, which is 0, converges to 0 times p, which is again a 0. So when alpha is 0, then the proof is very trivial. So you need not have to think, right? So for alpha is equal to 0, proof is trivial. Trivial means you need not have to think much, or it is very straightforward. Now we have to consider if alpha is not equal to 0. If alpha is not equal to 0, will the theorem will hold? Does the theorem will hold? That is what we have to show. So if alpha is not equal to 0, so it is given that xn converges to p. So that would imply for all epsilon greater than 0, there exists n naught belongs to natural number such that mod xn minus p less than epsilon for all n greater than equal to n naught. Let me call this as 1. What is my target? My target is to show that alpha xn converges to alpha p. A very obvious choice is I will consider modulus of alpha xn minus alpha p, and I will see whether it turns out to be less than epsilon or not. So let me consider modulus of alpha xn minus alpha p, which is same as alpha times xn minus p, which is same as mod alpha into mod xn minus p, which is same as, but xn minus p is less than epsilon. So what I'll get is mod alpha times epsilon. Now you could see that modulus of alpha xn is minus alpha p is less than mod alpha times epsilon for all n greater than equal to n naught. That should be noted. Now here mod alpha is unnecessarily it is coming. So I wanted to get rid of mod alpha. A trick could be, while writing this I will say that for every epsilon upon mod p greater than 0, mod epsilon, since alpha is non-zero, so mod alpha is positive and it is greater than 0. So you can see that mod alpha is not equal to 0, so mod alpha is strictly greater than 0. That should be noted. So epsilon upon mod alpha, here only I will epsilon upon mod alpha only I will write. Or some times people may not write this also, only they says that for every epsilon greater than 0, there exists del n naught belongs to natural number such that mod xn minus p less than epsilon upon mod alpha. You are allowed to adjust the epsilon. So here I can say mod alpha, then mod alpha will get cancelled. So what I'll get, mod alpha xn minus alpha p less than epsilon for all n greater than equal to n naught. This completes that sequence alpha xn converges to alpha p. This completes the multiplication, that scalar time sequence converges to scalar time limits. So in upcoming lectures we will prove that product of two sequence is convergent. Similarly, the reciprocal of a sequence is convergent provided the sequence is non-zero, and the ratio of the two sequences convergent. Very interesting could be, is the converse true? That we will definitely answer in a question. Is the converse true? Is the converse true? So if it is true, then you need to prove. If it is not true, then you have to give me a counter example. So please think over it. In a tomorrow's lecture, we will definitely discuss about the homework which I have given and the converse part, whether it is true or not. Thank you. Thank you so much.